Hello, my wonderful AP Statistics students. Welcome to another lesson in our unit on exploring one variable data. I'm Goldie and I'm here to take you through notes for today, talking about measures of center and spread. And this is going to get into our objective on summary statistics for a quantitative variable. So we're going to talk about all the measures of center today and most of the measures of spread as well. So if you're ready, go ahead and grab your notes, get settled in, and let's go through this content together. We're going to start by talking about measures of center. A measure of center attempts to use a single number to summarize a set of data. So we just got through talking about different graphs of data and how we can visualize data. Well, now we have an attempt to summarize data using a single number. There's three measures of center in statistics: mean, median, and mode. You might have heard the term average, of course. It's a generic term for a measure of center, but average is not a measure itself, okay? When people say average, they are usually talking about the mean of data, but in AP statistics, we are talking about mean, median, and mode. So do not call anything average, is what I'm trying to say there, okay? Let's talk about the mean, because that's the one you're probably most familiar with. Being a high school student now, you know everything about the mean because it's how your grades are calculated, right? In order to calculate the mean, you add up all the values in the data set and divide by the total number of values. Now, in our formula sheet, in math symbols, this is what it looks like. So we have our x bar equals capital sigma x sub I divided by n. Now, what does all of that even mean? Okay, so x bar represents the mean of a sample. And you notice how I'm pronouncing it x bar. That's what we call that. X bar, that represents the mean of a sample. X with a subscript of I is talking about each individual value in a data set. So think of I, think of individual. Okay. Now, what are we doing with each individual value? Well, that's where that capital sigma comes in. That talks about adding up. So it means we're going to add up each individual value of the data set is how we say that in math terms, right? And n represents the total number of values in a data set. Okay. So that's our formula for it, but you guys just probably know how to do it without the formula. Okay, so let's go back to this data set here where the data below represents the ages of a random sample of 24 teachers at our school. Here it is. What is the mean age of the teachers? So we can graph this. We know different ways to graph this, but let's say we want one number to summarize, okay, what's the mean age of teachers in our sample? Or what you might have said, what's the average age of teachers at our school? We can find the mean age by adding up all of those individual values. Okay, so each of them, and notice this notation right here, because there's a lot of teachers. If I want to show my work for this, I don't want to see you write out all 24 in a line in the numerator, okay? This is going to be our shorthand. We're going to have to do this a couple times in different formulas in this course. This is going to be shorthand for continue the pattern, right? That ... means continue the pattern between the values. So we're going to add up all of those individual values and then divide by 24 since there's 24 total teachers. So 820 divided by 24, we get 34.2 as the mean age of teachers in our sample. Okay. So while we use it most often, and we use it a lot in this course and in life, it's not the only measure of center. And most of the reasoning behind that is because it's unreliable around what we call outliers. Okay, let's talk about outliers first, and then we'll talk about why the mean is unreliable around it. Okay, an outlier is a value that lies some sort of abnormal amount of distance from the other values in your data set. Okay. Now, what is considered abnormal? It definitely depends on the data set, right? There's actually two mathematical ways of determining if a value is an outlier, and we're going to get to both of those ways later on, okay? But right now, let's just look at kind of an obvious example of an outlier. So suppose a student took 7 exams and had these scores, right? So they started off good, unit 1 test, unit 2 test, etc., 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 and then they have a 0, Okay. If I calculated in the gradebook the mean of these 7 scores, what would you get? Okay. Well, add them all up, divide by 7, you would get 78.3 as your score. Okay. So does a 78.3, does a grade of 78.3, if I said you had a test average or a test mean of 78.3, does that give a good idea of how you performed on your test? Probably not. Okay, you guys are probably going to be mad at me for that because there's a very clear outlier here, right? The 0 score. And in data sets, sometimes there's a legitimate reason to eliminate an outlier. So we want to be able to identify them because sometimes we can toss them out if we have a real reason to. Like, for example, why might you convince me to toss out the 0 as a test score? Okay, I don't know, maybe you were absent the day of the test and I put in a 0 because I never got a test from you, but you're like, hey, Goldie, I was absent, so can I just make up the test at a later date? I would say, of course, let me take off the 0, right? Like that's how it goes in the real world. Sometimes you can just toss out that outlier. There's other times where you can't toss out the outliers. They are a legitimate part of your data set that you have to interpret and examine. So it varies, right? Don't always throw out outliers, but sometimes you can, okay? Like in this case, I would gladly throw out the 0 for you on your test scores, assuming you would make up your test later, okay? So let's say I took your reason, whatever it may be, and I eliminated 0 from the grade book. What would be your new mean grade, right? How did getting rid of that 0 affect the grades, right? Your new mean grade. Well, if we took it off, our sum is 548. But now I only have 6 values because I took off that 7th value of a 0. And now my mean is 91.3. So in general, what did that mean do to, what did the outlier do to the mean in a data set? Well, what we saw was by taking the outlier out, my mean shot up, right? Because when I had the outlier in there, that outlier was pulling my test scores down with it, right? It was low, it was at the bottom, it was a 0, and it just wanted to pull down the average, okay? Join me, right, to down here below. And that's kind of the visual I want you to imagine when looking at outliers as they relate to the mean, is outliers pull the mean value to the outliers value. Okay, wherever they might be. In our test scores, the outlier was low, so it wants to pull the mean down with it. In a different scenario, the outlier might be higher than the mean, and if the outlier is higher than the mean, the outlier is going to try to pull the mean up to it. Okay. Now, this is in statistics is what we call a non-resistant measure. The mean is a non-resistant measure, meaning it's strongly influenced by extreme values. And I say extreme values here because non-resistant measures, they are affected by outliers, but they also just might be affected by extreme values that aren't mathematically considered an outlier, but are still extreme in nature, right? They're at the min or a max kind of boundary. A mean is greatly influenced by it. Okay. Now, we have other measures of center that are considered to be resistant, okay, that are not strongly influenced by those extreme values. And that's where our second measure of center, called a median, comes in. And this might also be something you've heard before, hopefully. Okay, but no judgment if you haven't. You're learning about it right now. It's a measure of center found by ordering data from the smallest value to the largest value, and then finding the middle value in the list. Okay, because that's kind of what a mean is supposed to do, right? The mean, you find, like, you want to kind of find the middle. Like when we were finding the average age of teachers, 34.2 was our mean. That we wanted that to be kind of in the middle of our data set. We expect that to kind of be in the middle. The median is the middle. If we were to put all the numbers in order, it would be the middle. It doesn't have a special symbol and formula like the mean does. We use MED on like the calculator and in some computer outputs and stuff to label the median, but it really doesn't have any special symbol, okay? So in an ordered list with an odd number, the median is the middle value. But if in an ordered list with an even number of values, the median is the average of the two in the middle, okay? The mean of the two in the middle, okay? So here's an example. So here's all of the teachers again, but now I've ranged them in order from smallest to largest. So lowest age to highest age. What's the median of the data set? Well, to find the median, you basically count inward, like, okay, 24, 51, they cancel, right? This is how I think of them as canceling, right? I count in one on this side, one on this side, one on this side, one on this side, okay? If you're a visual person, this is a good way to kind of get that middle value. You keep going until you get to these two middle values, okay? There's an even number of teachers, right? There was 24 teachers. That is an even number, which means to get to the middle of the list, you technically have like two numbers in the middle, right? So what's the median? Well, for the median here, you take the two numbers and divide it by 2. You find the mean, right? Which of course is 31.5. So it's the middle, the exact middle between those two values, okay? And that's going to be your median. If you had an odd number, like if you had 25 teachers, when you count in to find your middle value, it'll actually be like a single value, and that'll be your median. Okay? In this case, you had to average two numbers. Okay? And that's your median. The last one we're going to talk about, just because you've heard of it before, but we don't really cover it in AP statistics. It's not a learning objective in AP statistics, but I bring it up for, the knowledge. We're all about the knowledge here. The mode finds the most occurring value in a data set. And this comes from this idea of a mode being a measure of center, comes from the idea of having a symmetric unimodal distribution where the majority of your data is in the middle. Okay. And when that happens, your mode is in the center. However, because we're going to see so many shapes, there are so many shapes to different distributions, that the mode is kind of unreliable. It doesn't always occur in the middle like we anticipate it to. So for example, teacher ages. I know that the mean is 34.2. I know the median, I found it was 31.5, but what's the mode here, right? What's the most occurring data value? Well, that's going to be 29, right? Now, is 29 in the middle of my data set? Maybe not, okay? Again, this is just a number to try to summarize the data set. We can't really visualize it quite yet. But 29 is the mode. It's the most occurring. It happens 3 times. Now, you don't want me to get into the discussion of, can you have multiple modes, right? Like if I had 31 occurred twice, what if I had another teacher who was also 31? What if I had 3 teachers with 31 and 3 teachers with 29? Which one of those is the mode, right? Well, this is a hot topic in the statistics community, okay? Some teachers say, there's no mode, right? You can't have 2 most occurring values, therefore it's no mode. Some teachers will say, well, you have 2 modes now. You got two measures of center. Again, very widely debated. That's the kind of stuff we argue about in math courses here. But that's part of the reason why we don't use mode in this course, is because it's a little unreliable in terms of center, and there's still a couple questions about it. So you'll see us using mean and the median. Okay. All right, those are our measures of center. So now we get to jump over into measures of spread here. There's 4 common measures that we use in statistics: range, variance, standard deviation, and IQR. Okay. And all of these attempt to measure the variations of data in a distribution. So we have the measure of center, tried to get, the approximate center of the data. And then these are all ways that we measure the spread of the data. How spread out is your data from that center, which is why normally when we report a measure of center, we also report a measure of spread that goes along with it, because those 2 numbers together really give us a good summary of what the data is doing in our distribution. Okay. Oh, look there. That was my bullet point there. Measures of center give a good idea of the location. The spread gives us a good visual of how spread out the data is. Okay, so if we have the measure of center, maybe the spread or the variability is very small, or maybe we have a measure of center and the variability is very large. Okay, both of those distributions are going to look wildly different. Even if they have the same measure of center, having a small variability or having a very large variability is going to look a lot different and going to tell a different story. So we usually report these 2 numbers at the same time. Let's talk about range first, our first measure of spread. The range is the difference between the maximum and the minimum data value in a set. So we take the maximum and we subtract the minimum. We don't have a special symbol for range. We don't have a special symbol for max or min. We just call it max or min, but this is how you find it. Now, the one thing I see students mess up, the range is a single value. It's not an interval of values. So if your maximum was 30 and your minimum was 10, your range is not 10 to 30. Your range is 20. Okay. We say range is 20. Okay. So range is a single number, not an interval. And because it uses two values from the data set, it's very sensitive to those extreme values, right? Especially because outliers occur on either the min or the max side of your data set. So this is a non-resistant measure of spread. It is very sensitive to outliers, okay? But it's calculated fairly quickly, fairly easily. So it gives us a good idea of the data set variability in a quick way. Let's talk about standard deviation. Okay. The standard deviation is the average deviation of an observation from the mean of the data set. Okay. Average deviation of an observation from the mean. So we have a formula for it. It's probably going to be the most complicated formula you would have seen up to this point. Before I show it to you, though, I actually want to develop the formula by hand because I think it's really useful. Okay. Now, on the AP exam, you won't have to find the standard deviation by hand. It's never done by hand, actually. I'm going to have you do it a couple times in the homework maybe, but after I teach you how to do it on the calculator, you'll never have to do it by hand again. But for learning's sake, to really understand what the standard deviation is measuring, like what are we talking about when we're talking about average deviation, to really understand, I think this example is really going to help you, okay? So here's my go-to example here. A group of school children were asked how many pets they have at their home. And here are their responses arranged from highest to lowest, okay? Or lowest to highest, whatever. Here it is, right? Our first step to find the standard deviation is actually to calculate the mean, okay? And the mean number of pets is going to be 5 here in this sample, okay? So this is why statistics, standard deviation, and the mean go hand in hand, is because in order to find the standard deviation, you are actually going to be using the mean to get it, okay? So once we have the mean, let's look at these individual values again. So remember x sub I. So all of these are what we consider individual values. So the first thing we're going to do is calculate the deviations from the mean. Okay, so I'm going to take all of these individual values, I'm going to find the deviations, and I'm going to do that by subtracting the mean. So I'm going to take 1 minus the mean. That gives me -4. Then I'm going to take 3 minus the mean. That gives me -2. And I'm going to repeat that for all of these individual values, okay? And I'm going to get all of those deviations. So my deviations, -1, -2, and then all the way up from there, okay? Now what I'm going to do, okay, is square them. Now, why on earth would I square them, okay? Well, because if I wanted to add up these values, okay, because I just said standard deviation is the average deviation, okay? So if it's the average deviation, why don't I just take all of these deviations, add them up, and divide by the total number of deviations? Well, why didn't you go ahead and add all of those up? What number do you get? You get 0, in fact, okay? You get 0. Now, why do you get 0? Well, that's actually a property of the mean, okay? Fun fact, okay? If you take the deviation from each value, you subtract the mean from every value and add them all up, you will get 0, okay? That's a property of the mean. You'll get that for any data set. Isn't that kind of cool? I don't know. I think it's kind of cool. But we can't just add them up and divide by the total number of deviations, okay? That's not how we find it. So in math, what do we do to get rid of negative numbers? Because those negative numbers are really what's canceling out with the positive numbers to get us 0 for our average deviation. Well, the solution is either absolute value or square root, or excuse me, square. right? Both of those, if we do it to a value, they give us a positive number. If we do those to a negative, they give us a positive number. Now, for math reasons, you don't have to worry about, we can't really undo an absolute value once we take it, but we can undo a square. Once we take the square of something, we can undo it by taking the square root. And so that's kind of the direction we're going to go here. So I'm actually going to square all of these deviations, okay? Because if I take -4 and I square it, I get 16. If I take -2 and I square it, I get 4. And if I do that for all of those deviations, okay, all of them, even the positives, even 0, right? It all happens to all of them. I get now a bunch of square deviations, okay? Now with those squared deviations, okay, so I just copied them up here, okay? I didn't do anything new. These are all the squared deviations we just found. I'm going to add them up, okay? Because I want to find the average deviation. So I'm going to sum up the squared deviations. Let me add them all up. This is where the sigma part of the formula comes in. Okay, so far we have this as our squared deviations. Now I'm going to add them all up, and that's where sigma comes in. I'm going to add up all of those squared deviations, and in this example, I get 52. Okay, so I have 52, and then I'm going to take this value and divide it by n minus 1. Now, normally we divide by n to find the average, right? You're going to have to hold my hand and trust me when I tell you you're going to divide by n minus 1 here, okay? And I'm not going to explain the reason why. We're not going to get into it right now. The reason behind it has to do with a little bit more advanced math than we're ready for. Just follow me and go with me. You know, I know we normally divide by n, but just n minus 1 in this case, okay? We're going to take the sum of the squared deviations, divide by n minus 1. We had 9 students, so we're going to subtract 1 to get 8. And then we're going to take 52 divided by 8. We get 6.5, okay? So Goldie, we get 6.5. That is the average sum of the squared deviations, okay? The average sum, or I say average sum, is the average of the squared deviations. Average of the squared deviations. That value, 6.5, that's actually what we call the variance, okay? And it is a legitimate measure of spread. We don't talk about the variance too much in this course. We do talk about it a little bit later on. It is helpful, and we will revisit it, but not too much, okay? Variance comes into play a lot more in the calculus side of statistics. In the algebra side, where we're living, you know, we're having a good time over here, we don't use it as much, okay? But it is a stepping stone to get the standard deviation. I'm almost there. That value of 6.5, it has a special symbol s squared, variance. It's also s squared because it's the standard deviation squared. It's the average squared deviation. And of course, standard deviation is just the average deviation. We want to get rid of this squared piece. So how do we get rid of the squared piece? Okay. Well, to get back to the original units, to get back to the average deviation, we take the square root of the variance. Okay, so that's why it has this special symbol here. So the variance s squared is 6.5. I take the square root of that, and I get 2.55, and that gets the symbol s for standard deviation. Okay, so, and for those math visual peeps, this is my variance. If I take the square root of both sides, right, I get s equals 2.55. That's going to be the relationship between my variance and my standard deviation here, okay? Now the standard deviation, the units on standard deviation is going to be the same units as the original data set, okay? That's the same thing with the measure of center as well. I don't think I did a good job of reminding you. The units on measure of center are the same units as the data set. And that's going to be the same thing for the range in this situation. It's the same unit as the data set. So 2.55 pets, and we interpret the standard deviation here. This means that the number of pets typically varies from the mean on average by 2.55 pets. Okay. So we just built the formula for standard deviation. Okay, here it is, S equals. And look at that. That's beautiful. We know what all of those pieces mean. We know that X bar is the mean of a sample. xi represents each individual value in that data set. We know that sigma means add up. We know that n is the total number of values in the data set. And we know that S stands for standard deviation. You might also see that written as S sub x. It means the same thing. We use the subscript x because later on we're going to be getting into multiple sets of data, and we use subscripts like x and y to differentiate between the two sets of data, right? A subscript is just a label. It's not a mathematical operation. So we use S sub x sometimes. Okay? That's the formula for standard deviation. That's how we find it. It's on your formula sheet. You usually won't have to find, I say usually, you won't have to find it by hand. Maybe there'll be an odd multiple choice question here or there that kind of does something like it. But the formula is really important for remembering some of these facts about standard deviation. Okay? It measures the typical distance of the values in a distribution from the mean. It can only be used as the measure of spread when your mean is your chosen measure of center, right? So median and standard deviation don't go together. It is mean and standard deviation. It's always positive. It's only 0 when all the data values in the set are the same. Okay? So standard deviation is never negative, and it's only 0 when all the values are the same. It has the same units of measure as the original data set. It's non-resistant to extreme values, just like the mean is. Okay? Outliers greatly affect this. The greater the standard deviation is the greater the variation of the distribution. Okay? So if you have your values close together, you're going to have a small standard deviation because there's really not a lot of deviation from the mean. If you have a large standard deviation, then you're going to have greater variation because you're going to have values that are way different from the mean. Okay? Oh my gosh, and that was it. Oh, we're already at the end here, Goldie. I can't even believe it. We are having so much fun, but we're going to end on that note there. We're going to talk about IQR, which is the last of the measures of spread. We're going to talk about that in the next set of notes here. Okay, but that brings us to the end of this presentation. If you have liked this, please hit the like button and subscribe to my YouTube channel for more great AP statistics content. But until then, I wish you endless statistical success, and I will see you in the next video.